So it means that if I can find a feasible solution of this, as you can see, we have this constraint, linear constraint. So I can construct the feasible region. So y1, y2 satisfy this. It means that y1, y2 in these feasible regions. So as long as they are in y1, y2 in this feasible region, I can guarantee 48 y1 plus 20 y2 will always greater than equal to z bar, because that is the upper bound. That's the upper bound. Okay? Okay. So right now, we say that based on this discussion, we only know the 48 y1 plus 20 y2 is the upper bound. It's the upper bound of our z value. Okay. So that's what we say. I give you the primal problem. We don't know. We cannot find it. We cannot find this. And I want to utilize a discussion. Try to find a lower bound to find the upper bound, and if I can find them closer to get to each other, finally we can find these two bounds have the same value. It means that I find the optimum solutions. Okay. So in this discussion is that currently I utilize this method. Try to find the upper bound. But to find upper bound is not good enough. So we try to find the minimum of the upper bound. Okay? So that's why we try to find the minimum upper bound. So try to find the minimum upper bound. 48 y1 plus 20 y2. Okay, then we have a constraint. Constraint is based on this. Actually, it's this formulations. And we know that this formulation actually is linear programming formulations. And we call this is the dual of our primal problem. Okay. Okay. That's why I said, probably a long time ago when you learn the operations research, I tell you, I give you a primal problem and ask you to transform it to dual. Yes, you know how to transform it to dual. But the reason behind why we need this kind of transformation, we don't know that. Here we try to explain that to you. Okay, that's our reason. Okay, let's utilize this idea to apply them to another example. bit different from the previous one. Previous one, all of the constraints are less than equals to, but right now we have equality, we have greater than equals to, we have less than equals to. Previously we have all variable greater than equals to 0, but right now we have one is unrestriction. Unrestriction means that it can be positive value, could be negative value, or could be 0. Okay? So we, again, like the previous one, mark. Mark each constraint, 1, 2, 3. So we have 3 constraints. Okay? And systematically, we want to find the multiplier. So we have y1, y2, y3 for corresponding one. Okay? So it means that y1 multiplied by the first constraint, if it comes y1 y1 x1 plus
y1 x2
y1 x2
2y1
2y1 okay. And then y2 multiplied by the second constraint. Say again. 2y1.
2y2 x1.
Oh, sorry. 2y2 x1 minus
greater than equals to 3y2.
greater than equals to 3y2. But like the previous discussion, we hope we want to construct the upper bound, right? Right now, let's we want to construct the upper bound. So we hope we need the right hand side. We need the right hand side greater than the left hand side. So in this way, we can construct the upper bound. So if I want this result,
y2 should be minus.
right? Okay. And for the y, the third constraints. y3 x1 and y3 x2 and how about here y3 greater than equals to 0 like the previous one. Okay, so we only talk about y2 and y3, so let's go back to y1. That's equality. How about y1? Second, equal to 0. Are you sure? Positive value. Are you sure? Think about it. Suppose the left, it means that x1 and x2 is equal to 2, right? Right inside, right? Right inside, right? And we multiply by y1. We can multiply by 0, yes. We can multiply by positive value, yes. How about negative value? multiply by -2 or -1. Suppose y1 is -1. -1. No? Can we do that?
Yes.
Yes. So how about the value of our y1?
More restricted.
Could be any value. Okay? Okay. Okay, so right now since we want to construct the upper bound, so we want to add these three constraints together. So it becomes. The coefficient for x1 will be y1 plus y2 plus y3 for x1. And for x2, y1 minus y2 minus y3 plus 4x2. That will be less than or equals to. Two. We add these three constraints together. Let's do y1, right? Okay. Okay. So that's what we talk about is objective function. Our objective function. Two x1 cross x2. Right? Again, we need to construct the upper bound. So it means that I want to find the upper bound of this one, right? So it means that this one should be less than or equals to this one and less than or equals to. Okay. So how can I guarantee we can construct this red relation? What can I guarantee? This black one will be less than or equals to this one. Something minus. Say again? Are you sure? A little bit like what we do previously. We want to know, we want to construct it. We already systematically to find for the constraints, and we already add up that's here. Okay, and right now we just want to compare the objective function with this one. And once for some relation we can construct, then we can guarantee 2x1 plus 1x2 will be less than or equals to 2y1 plus 3y2 plus y3. The relation is that I need to guarantee the relation between these two and these two, right? Okay. The idea is that this break one should be less than or equal to this one. Once we can construct this relation, we know that less than or equal to this one. Right now is the idea. What's the relation between y1 to y2 plus y3 and 2? Greater than
Two.
why? Why?
Because they can eliminate x1.
Say again?
They can divide x1,
You can divide by x1.
and x1 is greater than 0.
Think about that. If x1 is less than 0. Yes, my question is, if here x1 is positive value, but if I say x1 is a negative value, think about that. If x1 is a negative value, what happens? It will be less than or equals to. Okay. Okay. This currently it is true because x1 is greater than or equals to 0. Okay, so the next one is we compare y1 minus y2 minus y3 and
Should be equal to.
be equals to y.
Because x1 is unrestricted, so
x2 or x1.
x2 is unrestricted, so
Because x2 is unrestricted, it could be positive value, it could be negative, it could be 0. Okay? So if I say less than or greater than or equals to, if it becomes negative value, we will to the opposite one. To avoid that, there's only one way it becomes equality. So you can multiply by any value. Okay?
okay.
If it is true, okay? So this one, just like what we previously defined, the double step, our constraint. We need to follow this constraint. Then y1, y2 will becomes feasible solution. Okay? Once this is true, then we can guarantee 2y1 plus y3 y2 3y2 plus y3. Once we can guarantee the y1, y2, y3 are feasible solution, then we can guarantee this one will be our upper bound, right? This one will become our upper bound. Okay. Okay. So right now we want to rewrite it again, and then transform this stuff to the dual of this. One more problem. Since that's upper bound, and we want to find the best one, so we want to minimize this upper bound. So here we just copy the constraint. We just copy from the double star. Okay. Do we have another constraint? For example, y1, y2, and y3.
Y1 unrestricted.
Here we already in the very beginning when we try to construct, we already have. So here y1 is unrestricted, y2 is less than or equals to y3 is. Okay. So generally for minimization or maximization we can for maximization we can find the upper bound, for minimization we can find the lower bound. Okay. So we just utilize this way to find it. But someone tried to summarize this rule, okay? We don't have to every time try to say well less than or equals to something, try to write a variable something. That's why in the very beginning I say if I ask you to transform them transform from one primal problem to a zero problem, you have one table to tell you how to do the transformation, whether it equals to something to a variable, something. So the following is the rule. Probably try to remember this table, but you don't have to, because in the very beginning of the problem we talk about maximization transform to minimization. So as you can see, all the variable greater than or equals to 0, then the minimization constraint will always greater than or equals to 1. So that's why what we have in the first example. And also in the example, we have maximization. All of the constraint is less than or equals to. So the dual problem, minimization problem, will always greater than equal. The variable will always greater than or equals to 0. Okay. So in the first example, actually already know this story. Okay. So in the opposite way, you can find it just in opposite direction. In the opposite direction compared to. Okay. So you only have to remember one of them, and the other one you already know in opposite way. And for unrestriction and equality, you don't have to remember that because for equality constraint, the variable will always the corresponding variable will always unrestricted. Okay, so okay, so the story of the maximization and minimization is maximize Cx. From this rule, it tells us that in the very beginning, I can just resequence the right hand side to the objective function coefficient, the objective function coefficient to the right hand side, and the rest of them we want to check the sign, the variable constraint. We just go back to this table, and this table will be one problem's variable will influence the dual problem's constraint. Again, correspondingly, one problem's constraint sign will influence this dual problem's variable sign. Okay. Okay. So let's use as the general rule to construct the following example. Okay, we'll minimize W is equal to 2y1 minus 3y2. And we have greater than equal to 1%, and less than equals to minus 2 equals to 4. Okay. It means I want to me to construct this. So that's why I say, maybe I'm not sure the sign of it, but I can just write down the coefficient first or right hand side first. So objective function would be prime is minimized, so the dual should be maximized, right? So that would be x1. Here it becomes our objective function coefficient. That's for x1, x2, and x3. Okay. And for the constraint, that will be the first constraint will be in this direction. So for sure, right hand side will be 2, right? For the first constraint, right hand side is 2. And the left hand side will be x1 minus x2. We determine that later. Then we go to the second constraint. The second constraint is here. The second column. The right hand side is minus 3. Okay? And okay, so here we have x1, x2, and x3. We want to determine that later. Okay, so we want to determine here.
So equal. First one is equal.
The first one is equal because y1 is unrestricted. Okay. Okay. How about you?
Less than equal to.
Because y2 is greater than or equals to 0. Less than or equal, right?
X1 is greater than 0.
Yes or no?
Yes.
No? Minimization. So we look at here and transform to here. Okay? Okay, here I didn't say this is prime or this is dual. No. When I try to do this kind of transformation, I only look at minimization and maximization. Okay, I don't care about which one is prime or which one is dual. Okay, so once we give you a minimization problem, it means that I want to check. I already have this information. I want to utilize this information to transform to this information. Okay. So how about x1?
Greater than equal to 0.
Greater than or equals to 0 because the first sign here, right? How about x2?
Less than equals to 0.
You don't have to check that because I previously said when they have opposite sign, then you know it's opposite relation. How about x3?
Unrestricted.
Okay. Which means that's what you learned before, right? That's what you have as a piece of paper. To construct, let's how to construct a dual problem. The next story is that previously we already tried to find for maximization. We tried to find the upper bound. And based on we try to find the upper bound, we in the following we find a dual problem. Okay.
Can we just transform the primal problem to normal form at initial and just convert it to the maximize, and we don't have to care about whether it is greater or smaller.
Standard form. So okay, it means that I want to transform them to maximization. Yes, we can do that. We can do it.
No, I mean that 我可以说中文，就是我可不可以先把它全部都弄成，就是假如说它是 minimize， 然后就把全部的 constraint 都弄成大于的样子，
可以啊，
然后这样再转。
可以啊。好啊，你要把它变成小一点的样子。
那个要放对我进去。
什么？
要
你要把它变成小于等于，你怎么会是 do？ I will explain that later.
要大米，
什么大米？
要把它拆成2个式子。
你还上过我的 OR 嘞？
对啊。
所以它就是要变成两个 constraint。如果要变成 standard form 就是这样子，然后我再把它，如果你要变成 standard form 的样子就是这样子，然后就是要变成 W。你要做的事情就是这样子。
对啊。
OK， 好，那会有多麻烦，你知道吗？可以，我可以这么做。我记得我们在大学的时候，我们有讲过说，我可以这么做，但是它很麻烦。就像这个原本的一个 constraint， 它就变成2个 constraint。那变成2个 constraint， 它变成第5之后就变成是2个 variable。但是这2个 variable 是有关系的。这2个 variable 其实是有关系的。那这2个 variable 其实后来又可以结合成哪个？
变 UI。
也会变 UIS。你就发现说，在某一个是大一点，你在另外一个是小一点，那就变成 UIS。可以这么做，但是它就变比较麻烦。这是为什么会出现 zero rule 的原因。我可以把它们全部转成 standard form， 转成 maximization 小的东西，可以，然后再做 transformation， 没问题。但是就会变得很麻烦，你要先把它们转成 standard form。OK， 另外一个问题是。
它就要拆成2个变数。
对，它就要拆成2个变数。OK， 可以用。We can do that. His question is like, can we just suppose there's a minimization in some of the constraint, not in the standard maximization form, because our maximization form looks like this. Maximize something. And all of the constraint equals to, and all of the variable. Can we do that? Because if that's a standard form, we can easily just transform them to some minimization. Just like first example. Yes, we can do that. The question is, you need to transform them first. For example, the minimization you have to transform to maximization multiplied by -1. Okay? And for the equality, you have to transform them to 2 constraints. Okay, since we need less than or equals to, so for this greater than 4, I have to multiply by negative value, and it becomes less than or equals to. Yes, we can do that, but it takes a lot of work. Okay? You can try. You can try. Actually, I encourage you to do that. And supposedly, in your undergraduate, you have to do that. Then you will observe that after you do the transformation, it really do a lot of work, but the result exactly the same, like this one, but a lot of work. So that's why someone will provide the general rule. So in the future, when we try to transform from some problem to a dual problem, we just follow the rule. Okay? We don't have to every time we don't have to transform them to maximization and then go back to minimization problem. We don't have to do that. That's why you have the general rule. Okay? Okay. If someone else asks me this question, I probably not curious. I would probably not surprised about it because it didn't reach my class in my undergraduate course before. But he asked me the question. I'm very surprised because I'm talk about that in undergraduate. I don't want to. Don't want to. Okay, I say originally I just want to find the upper bound for the maximization problem. And subsequently, based on the result, we can find the dual problem. Okay? Based on that discussion, we can find the dual problem. But question is, how can we construct or how can we know the relation between primal problem and dual problem? Previously, we only constructed the upper bound, right? And I also give you a figure to tell you the relation. Maximization, minimization, when we try to find optimum, we have exactly the same. That's how I tell you. And how can you prove that? I tell you this story, you probably say, yes, I see that before, yes. But the question is, how can you prove that? Right now, we want to utilize weak duality to prove the relation between the primal problem and the dual problem. And also, since we have weak duality, consequently we have strong duality. Okay? Okay, the x bar is a feasible solution of the maximization problem, and the y bar is a feasible solution of the minimization problem. I know we only talk about feasible solution, didn't talk about anything about optimal. We only talk about feasible solution. And maximization problem and the minimization problem are equal to each other. Okay. z value means that maximization the z value. When we plug in the x bar into the objective function, we can find the z value. The w value indicates the objective function value of the dual problem, the minimization problem. Okay? So z and the w indicates that. So in the future, I will utilize z indicates the maximization problem, the objective function value. The w indicates the minimization objective function value. Okay? And then next week, just show you that. Next week we will prove. We want to prove that. Oh, I think I will not rewrite it again. I will just continue that. Okay. So remember that. So any questions about this? No. See you next week. And have a nice spring break. And your homework.